There's something humbling about looking up at the night sky. Those countless pinpricks of light aren't just stars. They're fragments of a story billions of years in the making. A story we're only starting to decode. What if I told you that everything we see, the galaxies swirling in the darkness, the vast emptiness between them, even the fabric of space itself, might be part of a reality far stranger than we've ever dared to imagine? Welcome to a journey that will twist your perception of the cosmos inside out. Today, we're exploring 30 mind-bending perspectives on the cosmic fabric and the origins of space. Theories so profound, they'll make you question everything you thought you knew about the universe. Think about this for a moment. The space around you isn't just empty. It's a dynamic, ever-shifting stage where gravity warps the very rules of existence, where invisible forces tug at the seams of reality, and where the echoes of the Big Bang still ripple through the void. Scientists call it space-time, but what is it really? Is it a fabric, a fluid, or something beyond our current comprehension? And why does it exist at all? These aren't just philosophical musings, they're questions that cut to the heart of modern physics, and the answers might rewrite the textbooks. From the moment the universe burst into existence, it's been weaving its own epic tale, one filled with black holes that warp time, dark energy pushing galaxies apart, and dimensions we can't even perceive. But here's the most thrilling part. We're not just passive observers. With every telescope pointed at the heavens, every equation scribbled on a chalkboard, we're pulling back the curtain on the greatest show in existence. So if you've ever stared at the stars and felt that tug of wonder, that itch to know more, you're in the right place. This isn't just a video. It's a voyage to the edges of understanding, and trust me, you'll want to stay for every breathtaking revelation. The void between stars isn't the barren wasteland it seems. Look closer and you'll find a universe buzzing with hidden activity, like static on an old television screen, but for reality itself. Quantum physicists have discovered that so-called empty space is anything but empty. At the tiniest scales, particles and antiparticles flicker into existence for mere fractions of a second before annihilating each other. A phenomenon called quantum foam. It's as if the cosmos is constantly remaking itself in real time, a cosmic game of whack-aim, all where matter and energy trade places faster than we can measure. This isn't just theoretical strangeness, it has real-world consequences. The energy of these fleeting particles might explain dark energy, the mysterious force accelerating the universe's expansion. Picture a stretched rubber sheet with tiny springs pushing outward at every point, and you've got a crude analogy for how quantum fluctuations could be stretching space-time itself. Even gravity, the force that holds galaxies together, might emerge from this chaotic dance of virtual particles warping the fabric of reality beneath our feet. But here's where it gets truly mind-bending. Some theories suggest that what we call empty space is actually a sort of cosmic substrate, a fundamental medium that gives rise to everything: particles, forces, even the dimensions we experience. It's like realizing the air around you isn't just empty space but an invisible ocean, with currents and tides shaping everything that moves through it. If that's true, then the vacuum isn't just the backdrop of the universe. It might be the universe's most active participant, humming with possibilities we're only beginning to glimpse. So the next time you gaze at the night sky, remember, the darkness isn't passive. It's alive with potential, a canvas where the laws of physics paint in strokes we're still learning to see. And if we can decode its secrets, we might just uncover the universe's grandest masterpiece, written in the language of nothingness itself. The Big Bang feels like the ultimate beginning, a cosmic explosion that set everything into motion. But what if that moment wasn't the start at all? Some theories suggest our universe might be part of an endless cycle, like a phoenix perpetually rising from its own ashes. Imagine a big bounce, where instead of a fiery beginning, the universe collapses and rebounds over and over, stretching and compressing in an infinite loop. This idea turns the Big Bang from a one-time event into just another chapter in an epic saga of expansion and contraction. Then there's the multiverse theory, where our universe isn't alone. It's just one bubble in an endless sea of cosmic foam. Picture a pot of boiling water with new bubbles constantly forming, expanding, and sometimes even colliding. Each bubble could have its own laws of physics, its own version of reality. If that's true, then the Big Bang wasn't the birth of everything, just the moment our particular bubble of existence inflated into being. What's even wilder is that these ideas aren't just speculation. Cutting-edge physics like loop quantum gravity suggests that time itself might not have existed before the Big Bang. Instead of a singularity where everything breaks down, there could have been a quantum bridge from a previous universe, a cosmic handoff of space and matter. It's like discovering that the story we've been telling about the universe is just one volume in an infinite library. So when we look back at the Big Bang, we might not be seeing the beginning. We might be glimpsing a turning point in an endless cosmic dance. And if that's true, then the universe isn't just expanding. It's evolving, recycling, and rewriting its own history with every cycle. The question isn't just how it began, but whether it ever really began at all. Dark matter is the universe's best-kept secret, an invisible hand sculpting galaxies from the shadows. We know it's there because without its gravitational pull, stars on the edges of galaxies would fly apart like marbles spinning off a plate. Yet after decades of searching, we've never caught a direct glimpse of it. So what exactly is this mysterious substance making up over a quarter of everything in existence? One leading idea is that dark matter consists of undiscovered particles, something exotic like WIMP, or weakly interacting massive particles. These hypothetical particles would barely interact with normal matter, passing right through you like ghosts walking through walls. Scientists have built elaborate detectors deep underground, shielded from cosmic rays, hoping to catch the faintest whisper of a collision between dark matter and ordinary atoms. But so far, the detectors remain silent, leaving us to wonder if we're looking for the right thing. Then there's the wilder possibility: dark matter might not be particles at all. Some theories suggest it could be evidence of extra dimensions folded into the fabric of space, like cosmic origami we can't yet unfold. Imagine our three-dimensional universe as a sheet of paper, but there are other sheets stacked invisibly alongside it, each with its own physics. The gravity from those hidden dimensions might leak into ours, appearing as the extra pull we call dark matter. Even more radical is the idea that dark matter could be remnants of parallel universes brushing against our own. Picture two soap bubbles floating in space. Where they touch, matter from one might seep into the other, leaving traces we perceive as this elusive substance. If true, dark matter wouldn't just be a cosmic mystery, it would be our first tangible connection to realities beyond our own. The search for answers continues, with telescopes mapping dark matter's gravitational fingerprints and particle colliders probing the frontiers of physics. Every null result, every unexpected signal, brings us closer to rewriting the rules of reality. Because dark matter isn't just missing mass, it's a clue, a cosmic breadcrumb leading us toward a deeper understanding of how the universe truly works. And when we finally uncover its nature, it won't just solve a puzzle, it could reveal an entirely new layer of existence. dark energy is the universe's silent rebel, working against gravity's pull to push galaxies apart at an ever-increasing pace. While dark matter holds cosmic structures together, dark energy does the opposite, stretching the fabric of space-time like an invisible hand tugging at the edges of reality. Scientists first stumbled onto this mystery in the late 1990s when they discovered that distant supernovae were dimmer than expected, revealing an expansion that wasn't slowing down, it was speeding up. This wasn't just a surprise, it was a cosmic curveball that forced us to rethink everything we thought we knew about the fate of the universe. So what could dark energy actually be? One leading theory suggests it's the energy of empty space itself, a property Einstein once called the cosmological constant. Imagine space as a vast, invisible ocean where new water keeps appearing between the waves, forcing them farther apart. But here's the catch. If this energy stays constant while the universe expands, its influence grows over time, making the acceleration unstoppable. Another possibility is that dark energy isn't constant at all. It could be a dynamic force field, shifting and evolving like weather patterns in the cosmos. Some models even propose it's tied to an undiscovered particle or a fifth fundamental force, something entirely outside our current understanding of physics. Then there's the most dramatic scenario, the Big Rip. If dark energy's strength increases indefinitely, it could eventually overpower every force in nature. Galaxies would be torn apart first, then stars, then planets, and finally even atoms themselves, shredded into a cold, formless void. It's a haunting vision, but not necessarily our destiny. The truth might be stranger still. Dark energy could fade away, reverse direction, or even trigger a new phase of cosmic evolution we can't yet imagine. What makes this puzzle so thrilling is that dark energy isn't just some distant abstraction. It's shaping the universe's fate right now, dictating whether trillions of years from now, galaxies will still glow with starlight or vanish into eternal isolation. Every observation, from galaxy surveys to deep space telescopes, brings us closer to unraveling this enigma. And when we do, we won't just solve a mystery, we'll rewrite the story of everything. What if everything you see around you, the stars, the planets, even your own hands, isn't truly three-dimensional? The holographic principle turns our understanding of reality inside out, suggesting that the universe might be a vast, incredibly detailed projection. Imagine a movie screen, but instead of flat images, it generates an entire immersive world complete with depth, texture, and motion, except the screen, in this case, is the two-dimensional boundary of the cosmos itself. Every particle, every force, every event we experience could just be shadows cast from information etched onto this distant, invisible surface. This isn't science fiction. It's a serious theory born from the clash between quantum mechanics and Einstein's general relativity. Black holes played a key role in its discovery. When physicists calculated how much information a black hole could contain, they found something bizarre. The maximum data it could hold wasn't proportional to its volume but to its surface area. It's like realizing a hard drive's storage capacity depends on the size of its casing, not the space inside. This odd result led to a shocking idea. What if everything obeys this rule? What if the universe itself is storing its data on a cosmic hard drive we can't see? The implications are staggering. If the holographic principle is true, then our tangible, three-dimensional world is an illusion. A high-resolution hologram generated by quantum bits flickering at the edge of existence. Think of it like a video game. The graphics you see on screen aren't the real action. They're just a visual representation of code running somewhere else. In this case, the code might be written in the fabric of space-time, with gravity and quantum fields acting as the software rendering our reality. But here's where it gets even stranger. If the universe is a hologram, then time and space as we know them could be emergent properties, not fundamental truths. Just as pixels blend together to form an image, our perception of depth and movement might arise from deeper, more abstract processes. This could explain some of physics' biggest mysteries, like why quantum particles seem to know what distant particles are doing, a phenomenon Einstein called spooky action at a distance. If everything is interconnected at the informational level, then entanglement might just be the universe reading from the same line of code. Skeptics argue that the holographic principle is untestable, but experiments are already underway. Scientists are using precision lasers to hunt for pixelation in space-time, tiny, grain-like fluctuations that would betray the universe's underlying digital nature. Others are studying the cosmic microwave background, the afterglow of the Big Bang, for patterns that might reveal a holographic signature. Even if the theory isn't confirmed, it's reshaped how we think about reality, blurring the line between the physical and the informational. So the next time you reach out to touch something solid, ask yourself, are you feeling an object or just decoding a message from the edge of the universe? If the holographic principle holds, then reality isn't what it seems. It's a masterpiece of cosmic engineering, painted on the canvas of space-time itself. And if we can crack its code, we might finally understand why the universe looks the way it does, from the smallest quark to the largest galaxy. Time might feel like the most constant force in our lives, the steady tick of a clock, the inevitable march from birth to death. But Einstein shattered that illusion over a century ago, proving time isn't absolute. It stretches and compresses like taffy, depending on how fast you're moving or how close you are to a massive object. Yet even this revolutionary idea might only scratch the surface of time's true nature. What if time isn't a fundamental part of the universe at all, but something that emerges from deeper, more mysterious processes? Take a step down to the quantum level and time starts to behave strangely. In the world of particles and waves, equations often work just as well whether time flows forward or backward. Some physicists argue this isn't a quirk of math, but a clue time might not exist in the quantum realm. Instead, it could be a collective illusion, like the sense of motion in a flipbook. Each page is static, but flip them fast enough, and your brain stitches them into a fluid story. Similarly, time might arise from the way quantum systems interact, creating the appearance of change where none fundamentally exists. This idea leads to the block universe theory, where past, present, and future are equally real, fixed like frames in a film reel. In this view, your birth, your life, and even your distant death all exist simultaneously, locked in place like landmarks on a map. The feeling of now is just your consciousness moving through this frozen landscape, like a flashlight beam scanning across a darkened room. It's a chilling thought. Free will, the passage of moments, even the urgency of deadlines might all be artifacts of perception, not the universe's true structure. But how could something as visceral as time be an illusion? Think of temperature. We feel hot and cold as real properties, but zoom in, and they disappear, replaced by the frenetic dance of molecules. Time might be the same, a macroscopic effect of microscopic chaos. Some theories even suggest that entropy, the tendency of systems to disorder, creates the arrow of time by giving events a preferred direction. Without it, the universe might be a timeless jumble where cause and effect blur into irrelevance. The implications are staggering. If time is emergent, then black holes, where time seemingly grinds to a halt, might not be anomalies but windows into the universe's timeless foundation. Near a singularity, the illusion could unravel, revealing reality as it truly is, static, unchanging, and profoundly alien. even our attempts to unify gravity and quantum mechanics hit snags because one treats time as dynamic, the other as optional. Solving this rift could require rewriting time's role entirely. So the next time you check your watch, remember, those seconds ticking away might be more like ripples on a pond than a river flowing inexorably forward. The universe could be a frozen sculpture, and time, the grand, unshakable force guiding our lives, might just be the light we're using to see it. What if our universe is just one page in an infinite cosmic library? The multiverse hypothesis suggests exactly that, a staggering reality where every possible version of existence plays out somewhere, from worlds nearly identical to ours to realms so bizarre they defy comprehension. This isn't science fiction. It's a serious scientific idea with roots in quantum mechanics, where particles exist in multiple states until observed. At the cosmic scale, this many worlds interpretation implies that every decision you make spawns new universes, one where you took that job offer, another where you never existed at all. But quantum branching isn't the only path to parallel worlds. Cosmic inflation, the theory that our universe expanded exponentially in its first moments, could have created countless bubble universes beyond our observable horizon. Picture a pot of boiling water. Each bubble represents a separate cosmos with its own unique physics. Some might have stronger gravity, making stars burn out in seconds. Others could lack dark energy, collapsing back into singularity before life ever sparks. And somewhere out there, a bubble might be so similar to ours that your alternate self is watching this video right now, wondering the same thing. String theory takes this even further, proposing that extra dimensions curled up so tiny we can't detect them could harbor entire universes just millimeters away, separated by folds in space-time we'll never perceive. It's like living in a vast apartment building where each unit has different rules. One allows light to move slower, another has 5 fundamental forces instead of 4. The catch: these dimensions are locked away, their realities forever out of reach. Then there's the ultimate mind bender, the mathematical multiverse. If the universe is fundamentally mathematical, as some physicists argue, then every possible equation describes a real, physical world. There could be a cosmos where pi equals 4, where triangles have 4 sides, or where time runs backward. These aren't just thought experiments, they're testable ideas. Scientists scour the cosmic microwave background for bruises left by collisions with other universes, while particle accelerators hunt for evidence of extra dimensions. The multiverse isn't just about quantity, it's about possibility. It reshapes how we think about existence, turning the universe from a single masterpiece into an endless gallery of realities, each with its own story. Whether you find it exhilarating or unsettling, one thing's certain: if even a fraction of this is true, reality is far stranger and far richer than we ever dreamed. Imagine 2 coins flipped on opposite sides of the galaxy. No matter how far apart they are, they always land matching sides up. That's the eerie magic of quantum entanglement, where particles become so deeply linked that measuring one instantly defines the state of its partner, even if they're separated by billions of light years. Einstein famously dismissed this as spooky action at a distance, refusing to believe the universe could allow such instantaneous connections. Yet experiments have proven him wrong time and again, leaving us with a reality far stranger than even he envisioned. This phenomenon isn't just a laboratory curiosity, it might be the glue holding the cosmos together. When particles become entangled, they don't merely share information faster than light, they defy our everyday notions of separateness. It's as if the universe has an invisible phone line running through it, connecting everything in a web of instant communication. Some physicists speculate that entanglement isn't an exception but the rule, that space-time itself could be woven from countless quantum threads linking every particle, every star, every galaxy in a vast hidden network. Think of it like a cosmic game of dominoes where tipping one piece affects all the others simultaneously, not because something travels between them, but because their fates were intertwined from the start. This could explain why black holes, those cosmic vacuum cleaners, don't just destroy information when they evaporate. Entanglement might preserve it, stitching the fabric of reality back together behind the scenes. Even the way galaxies cluster across the void could hint at quantum connections operating on scales we're only beginning to fathom, the wildest part. Entanglement might not require any action at all. In a universe where space and time are emergent properties, what we perceive as distance could be an illusion. Particles aren't sending signals faster than light, they're simply parts of a deeper, unified whole, like separate ripples on the same pond. This idea, called quantum monism, suggests that at the most fundamental level, everything is one. The separations we see between you and your chair, between Earth and the farthest quasar, are just surface-level appearances, like waves forgetting they're made of the same ocean. Experiments are already pushing the limits of this mystery. Scientists have entangled particles over record distances, even using satellites to beam photons across continents. Others are testing whether gravity itself emerges from quantum entanglement, a theory that could finally bridge Einstein's relativity with the quantum world. If they're right, then every time you feel the weight of your body or watch an apple fall, you're witnessing the ghostly hand of entanglement at work. So the next time you hear someone call entanglement spooky, remember it might not be the universe that's strange, but our limited perspective. What if the real magic isn't the connection between far-flung particles, but the revelation that they were never truly apart to begin with? Black holes are nature's ultimate enforcers of cosmic censorship, regions where gravity becomes so overpowering that the universe itself seems to draw a curtain, hiding whatever lies beyond the event horizon. Step across that invisible boundary, and the ordinary rules of reality dissolve. Time slows to a crawl, space stretches into an infinite descent, and the very fabric of existence twists into knots. But here's the real mystery. Where does it all lead? Some theories propose that black holes aren't just dead ends, but tunnels, wormholes stitching distant corners of spacetime together, or even birthing entirely new universes in their depths. Take the idea of black holes as cosmic recyclers. When matter collapses into a singularity, the extreme conditions might trigger a rebound, a sort of quantum bounce. Instead of vanishing into oblivion, the compressed remains could explode outward, spawning a fresh universe with its own laws of physics. Picture a seed buried in soil. What looks like an end from one perspective is the beginning of something entirely new. This isn't just speculation. Equations in loop quantum gravity suggest singularities might not be infinitely dense, but reach a point where gravity repels rather than attracts, turning collapse into creation. Then there's the information paradox, a puzzle that's divided physicists for decades. If black holes swallow stars, planets, and light, what happens to all that information? Quantum mechanics insists it can't be destroyed, yet general relativity claims it's irretrievably lost behind the event horizon. The conflict has sparked wild ideas like holographic storage, where data isn't erased but smeared across a black hole's surface like cosmic graffiti. Others argue that information leaks back out via Hawking radiation, the faint glow black holes emit as they evaporate. Imagine burning a book and claiming its words survive in the smoke. That's the scale of the conceptual leap we're grappling with. But the boldest theories turn black holes into bridges. If two entangled black holes link distant regions of spacetime, crossing one could spit you out somewhere or someone else entirely. It's like stepping into an elevator and discovering the buttons don't just go up and down but across dimensions. The catch, surviving the trip, is another matter. Tidal forces near the singularity would stretch you into atomic spaghetti, while quantum effects might scramble your very structure. Yet mathematically, the possibility remains, a tantalizing hint that these cosmic monsters could be less like graves and more like revolving doors. What's clear is that black holes aren't just astrophysical oddities. They're laboratories for the most extreme physics imaginable. Every observation, from gravitational waves rippling out of their collisions to the eerie shadows they cast against starlight, brings us closer to answers. And when we finally decode their secrets, we won't just understand black holes. We'll glimpse the universe's deepest workings, written in the violent swirl of space-time itself. If black holes are the universe's ultimate vacuum cleaners, sucking in everything that crosses their path, then white holes would be their cosmic opposites, fire hydrants blasting matter and energy outward with unstoppable force. These hypothetical objects, first imagined as mathematical solutions to Einstein's equations, aren't just theoretical curiosities. They could hold the key to understanding the most explosive event in history, the Big Bang itself. Picture a black hole running in reverse where nothing can enter, only escape, and you've got the essence of a white hole. But here's the twist: if a white hole existed, it wouldn't just be an oddity. It might be the birthplace of our entire universe. The idea isn't as far-fetched as it sounds. Some physicists propose that the Big Bang wasn't a singular explosion from nothingness, but the eruption of a white hole, a cosmic reboot triggered by the collapse of a previous universe. Imagine a black hole in another reality collapsing into a singularity, only to rebound as a white hole in ours, spewing out the raw material for galaxies, stars, and eventually life. It's a poetic symmetry, creation and destruction linked in an endless loop, like a cosmic heartbeat. This, a big bounce scenario, turns the universe into a phoenix, eternally dying and rising from its own ashes. What makes white holes so tantalizing is their potential to solve one of cosmology's biggest puzzles, the singularity problem. Black holes famously crush matter into infinitely dense points where physics breaks down, but white holes could offer an escape. Instead of a dead-end singularity, matter might emerge reborn, like a scrambled message decoded on the other side. The math even suggests that a black hole in one universe could connect to a white hole in another via an Einstein-Rosen bridge, a wormhole stitching two realities together. It's as if the universe keeps a backdoor open, ensuring nothing is ever truly lost, just transformed. Yet for all their theoretical appeal, white holes face a glaring challenge. We've never seen one. Unlike black holes, which announce their presence by bending light and devouring stars, white holes would be fleeting phenomena. Their explosive nature means they'd likely self-destruct in a blaze of radiation, leaving behind only echoes. Some researchers speculate that gamma-ray bursts, the most energetic explosions in the cosmos, could be white holes popping into existence and vanishing just as quickly. Others wonder if dark matter, that invisible scaffolding holding galaxies together, might be the faint afterglow of ancient white holes, their remnants lingering like cosmic graffiti. The most radical implication: if white holes exist, time itself might work differently inside them. While black holes trap everything behind an event horizon, white holes could have anti-event horizons, barriers that only allow outward movement. Step too close and you'd be hurled away at impossible speeds, as if the universe itself were rejecting you. This bizarre behavior hints at a deeper truth. The laws of physics might not just bend at these extremes, they could flip entirely, revealing a hidden symmetry between past and future, input and output. Whether white holes are real or just mathematical ghosts, they force us to confront the universe's grandest symmetries. If black holes represent endings, white holes suggest beginnings, two sides of the same cosmic coin. And if our universe really did emerge from one, it wouldn't just reshape our origin story. It would mean that every star, every planet, every one of us is part of something far larger, an infinite cycle of collapse and rebirth, where death is just another word for transformation. Wormholes sound like the stuff of science fiction tunnels burrowing through the fabric of space-time, connecting distant stars or even different eras with a single step. Yet these cosmic shortcuts aren't just fantasy. They're hidden in the equations of Einstein's general relativity, lurking as valid solutions to the laws of physics. Picture space-time as a sheet of paper folded in half. Punch a hole through both layers, and you've got a crude model of a wormhole, a bridge between points that would otherwise take billions of years to cross. But here's the catch: while the math allows them, nature seems to resist. Wormholes, if they exist at all, would be wildly unstable, snapping shut the instant anything tried to pass through. That's where exotic matter comes in, a hypothetical substance with negative energy that could prop a wormhole open long enough to traverse it. Imagine exotic matter as cosmic duct tape, counteracting gravity's crushing grip to keep the tunnel from collapsing. Unlike anything we've found in nature, this strange material would defy common intuition, pushing rather than pulling when subjected to gravity. Some theories suggest quantum effects, like the Casimir effect, where closely spaced metal plates create a tiny region of negative energy, might hint at how such matter could exist. But producing enough to stabilize a wormhole, that's a challenge even our most advanced engineering can't yet fathom. The implications of traversable wormholes are staggering. A tunnel linking Earth to Proxima Centauri could turn a 4-year light-speed journey into a stroll across the threshold. Even wilder is the possibility of time travel. Because wormholes connect not just locations but moments in space-time. Entering one end while the other moves at relativistic speeds could create a gateway to the past or future. It's like having two clocks synchronized at either end of a tunnel. Shake one, and the other ticks out of sync, creating a doorway through time itself. But before you start drafting letters to your past self, consider the paradoxes. The infamous grandfather paradox, where traveling back to prevent your own birth would erase your ability to time travel, hints at the universe's allergy to contradictions. Some physicists argue quantum mechanics might resolve these loops, allowing only self-consistent timelines where actions in the past align with the future that enabled them. Others think wormholes simply self-destruct the moment paradoxes arise, like a cosmic circuit breaker tripping to preserve causality. The search for real wormholes isn't just theoretical. Astronomers have proposed looking for their gravitational fingerprints, unusual distortions in starlight, or inexplicable lensing effects where light bends around invisible tunnels. Some even speculate that certain black holes might secretly be wormhole mouths, their event horizons masking passageways to elsewhere. If that's true, then the supermassive monsters at the centers of galaxies could be less like dead ends and more like bustling intergalactic terminals. Whether wormholes are out there or forever confined to chalkboard equations, they force us to confront the universe's deepest symmetries. They whisper that space and time might not be rigid scaffolding but flexible, dynamic, and full of hidden doorways. And if we ever unlock their secrets, the cosmos wouldn't just feel smaller. It would become a labyrinth of endless connections waiting to be explored. What if the universe around us, with its swirling galaxies, the laws of physics, even your own thoughts, isn't the base layer of reality, but an elaborate simulation running on some unfathomably advanced computer? This isn't the plot of a sci-fi movie. It's a legitimate hypothesis debated by philosophers and physicists alike. At its core, the simulation argument suggests that if civilizations eventually develop the power to create conscious, hyper-detailed simulations of their ancestors, the number of simulated minds would vastly outnumber the real ones. Statistically speaking, the odds that we're the original biological beings shrink to almost zero. In other words, if simulated universes are possible, we're almost certainly living in one. Think of it like this. Imagine a video game so advanced that the characters inside it aren't just scripted animations but self-aware entities, convinced they're living in a real world. Now scale that up instead of a game console. Picture a civilization with computing power billions of times beyond ours, capable of rendering every quark, every photon, every ripple of gravity with flawless precision. To the simulated beings inside, their reality would feel as solid and undeniable as ours does to us. The cosmic fabric we study, the curvature of space-time, the dance of particles, might just be lines of code executing in a higher dimensional processor. But how could we ever test such a radical idea? Some scientists propose looking for glitches or shortcuts in the simulation's rendering. Just as a video game simplifies physics in distant background objects to save processing power, our universe might have detectable approximations, tiny inconsistencies in energy levels, statistical anomalies in quantum behavior, or even limits to how small we can measure spacetime. Others suggest that if the simulation has a resolution limit, like pixels on a screen, we might find it at the Planck scale, the smallest meaningful unit of measurement in physics. Even more intriguing is the notion that cosmic rays or high-energy particle collisions could reveal the simulation's underlying computational framework, like catching a glimpse of the code behind the graphics. Then there's the existential twist. If we're in a simulation, who's running it? Are we someone's historical reconstruction, a research project, or an ancestor simulation created by our own distant descendants? And what happens if we ever develop the technology to create conscious simulations ourselves? Would that make us the programmers, or just nested layers in an infinite digital onion? The simulation hypothesis doesn't just challenge our understanding of reality. It reframes the very meaning of existence, turning the universe into a cosmic Matryoshka doll with no guarantee of an outermost layer. Skeptics argue that the idea is untestable metaphysics, but its implications are too profound to ignore. If true, it could explain some of physics' deepest puzzles, like why the universe's constants seem finely tuned for life, or why quantum particles exist in probabilistic states until observed. After all, in a simulation, these might just be optimization choices or lazy loading techniques to conserve resources. Even consciousness itself, the hard problem that baffles neuroscientists, could be a feature of the software rather than an emergent property of biology. So the next time you feel the sun on your skin or gaze at the stars, ask yourself, are you experiencing the unfiltered cosmos or just the most immersive simulation ever conceived? Whether the answer terrifies or exhilarates you, one thing's certain: the universe just got a lot more interesting. And if we are living in someone else's code, the real question isn't, are we simulated? But what happens when we start noticing the seams? The universe is unimaginably vast, with billions of galaxies, each containing billions of stars. Statistically, the odds seem overwhelming that life should have arisen elsewhere, perhaps countless times. So why, in all our searching, have we found only silence? This is the Fermi paradox, a puzzle that's haunted scientists for decades. If the cosmos is so teeming with potential, where is everybody? One unsettling possibility is that civilizations tend to self-destruct before they can spread across the stars. Imagine a species like ours, harnessing the power of the atom, mastering biotechnology, even flirting with artificial intelligence only to succumb to war, environmental collapse, or runaway technology. It's a sobering thought. The Great Filter, a hypothetical barrier that prevents life from progressing beyond a certain point, might not lie in our past but in our future. If true, the eerie quiet of the universe could be a warning, a graveyard of worlds that never made it. But what if the answer isn't doom but transformation? Advanced civilizations might evolve beyond the need for physical bodies, uploading their consciousness into machines or even merging with the fabric of space-time itself. To them, planets and stars could seem as quaint as caves do to us relics of a primitive stage. They might communicate in ways we can't detect, using neutrino bursts or quantum entanglement instead of radio waves. The universe could be buzzing with activity, just on a frequency we're too young to tune into. Then there's the zoo hypothesis, the idea that extraterrestrials are deliberately avoiding us, treating Earth like a nature preserve or a lab experiment. Just as we might observe uncontacted tribes from a distance, advanced beings could be watching, waiting for us to reach a certain milestone before making contact. Others speculate we're living in a cosmic backwater, a quiet neighborhood far from the bustling interstellar highways where civilizations trade and clash. The darkest explanation, we might truly be alone. The conditions for life could be so staggeringly rare that despite the universe's scale, we're the first or the only ones to emerge. The silence wouldn't be a mystery but a reflection of our extraordinary luck. Whatever the truth, the Fermi paradox isn't just about aliens. It's a mirror, forcing us to confront our own place in the cosmos and what might lie ahead, whether we're destined to fade into the void or finally hear a voice calling back. Picture this, a tiny microbe no bigger than a speck of dust, clinging to a chunk of rock hurtling through the void of space. For millions of years, it survives the freezing vacuum, the blistering radiation, the crushing pressures of cosmic winds until one day, its ride crashes into a young, watery planet called Earth. That microbe wakes up, finds a hospitable home, and begins to multiply. Fast forward 4 billion years, and its descendants are reading these words. This isn't just science fiction, it's the bold idea of panspermia, the theory that life didn't start here at all but arrived pre-packaged from the stars. The concept isn't as far-fetched as it sounds. We already know space is littered with organic molecules, the building blocks of life floating in vast clouds between stars or embedded in asteroids. Some microbes, like the ultra-tough tardigrades, can survive extreme conditions that would kill almost anything else, including years of exposure to space. Experiments on the International Space Station have shown bacteria clinging to the exterior, weathering the harsh environment as if it were just another day at the office. If life can endure out there, even for a while, why couldn't it hitch a ride on a comet or meteorite, traveling from one world to another like a cosmic stowaway? The math gets even more intriguing when you consider how much material gets exchanged between planets. Mars, for example, regularly flings debris into space during asteroid impacts, and some of those rocks eventually land on Earth. We've even identified Martian meteorites right here on our own planet. If microbes existed on Mars billions of years ago, when it was warmer and wetter, they could have made the trip, seeding life here after a journey of millions of years. It raises a wild possibility. Instead of life arising independently on Earth, we might all be Martians at heart, but panspermia doesn't stop at our solar system. Some versions of the theory suggest life could spread between star systems, even galaxies, aboard rogue planets' worlds ejected from their orbits, drifting through interstellar space like nomadic arcs. These wandering worlds, shielded by thick ice layers, might carry frozen microbes across unimaginable distances, depositing them onto new planets when they're captured by another star. The universe could be engaged in a slow-motion game of biological ping-pong, with life bouncing from one corner of the cosmos to another over billions of years. The implications are staggering. If panspermia is true, life might not be a rare fluke but a cosmic inevitability, popping up wherever conditions allow and spreading like dandelion seeds in the wind. It would mean the difference between a universe where life is a lonely accident and one where it's a persistent, almost viral phenomenon, threading its way through galaxies. Some scientists even speculate that life could have originated near the center of the galaxy, where radiation and turbulence might have provided the energy needed for complex chemistry before hitching rides outward to quieter neighborhoods like ours. Of course, the big question remains, where did it all start? Panspermia doesn't solve the mystery of life's ultimate origin. It just pushes it farther away, onto some distant world or even an earlier epoch of the universe. But that's part of its beauty. If we're all descendants of interstellar travelers, then the search for our roots isn't just a planetary endeavor, it's a galactic one. Every microbe, every plant, every person might carry within them the legacy of a journey that began among the stars. So the next time you look up at the night sky, remember, you might not just be gazing into the cosmos. You might be staring at your oldest family photo. Here's a chilling thought. What if you're not a person reading this right now, but a momentary flicker of consciousness, a self-aware accident conjured from the random jostling of atoms in an otherwise lifeless void? That's the essence of the Boltzmann brain, a thought experiment so unsettling it makes the simulation hypothesis seem almost cozy. Named after physicist Ludwig Boltzmann, the idea hinges on a simple but staggering statistical quirk. In an infinite universe where particles randomly arrange themselves over eternity, it's far more likely for a single, fully formed brain complete with false memories of a past and an imagined environment to spontaneously assemble than for an entire ordered cosmos like ours to exist. Think of it like shaking a box of alphabet soup for eternity. Eventually, the letters will spell out a perfect sonnet purely by chance. Now scale that up. Given enough time, quantum fluctuations in a lifeless void could, statistically, spit out a conscious mind that believes it's lived a full life in a rich universe, only to dissolve back into chaos moments later. The odds of your entire lived experience being real are astronomically worse than you being that fleeting aberration. It's the ultimate existential prank, a universe where the most probable you isn't a biological entity with a history, but a phantom thought blinking in and out of existence. But why does this matter? Because it exposes a razor's edge in our understanding of reality. If the universe is eternal and random, Boltzmann brains should outnumber real, evolved minds like ours by an unimaginable margin. So why does everything feel so consistent? Either we're spectacularly lucky to exist in a cosmos where order prevails, or there's a deeper principle at work, something that tilts the scales away from chaos. Some physicists argue this is evidence for the anthropic principle. The universe must have properties that allow observers like us to exist, because otherwise no one would be here to question it. In other words, the fact that we're having this discussion at all suggests reality isn't a dice roll, it's rigged in favor of consciousness. The implications spiral even further when you consider quantum mechanics. In a world where particles exist in probabilistic states until observed, could the act of perception itself be what stabilizes reality? If a Boltzmann brain formed, would its observations collapse quantum possibilities into a false but coherent world? It's as if the universe is playing a game of chicken with itself, teetering on the edge of nonsense, only held together by the sheer insistence of observers like us. Skeptics counter that the Boltzmann brain paradox is a reductio ad absurdum, a sign that our assumptions about infinity or quantum fluctuations are flawed. Maybe the universe isn't eternal, or perhaps there's an undiscovered law that prevents such freakish order from chance events. Others propose that consciousness isn't something that can be accidentally assembled like a Lego set. It might require a specific, irreducible complexity that randomness can't muster. Yet the thought experiment lingers like a shadow, forcing us to confront the fragility of our place in the cosmos. Are we the improbable survivors of a cosmic lottery, or is reality far stranger, a stage where the audience and the play are locked in an inseparable dance? The next time you recall a childhood memory or feel the sun on your skin, ask yourself, is this the tapestry of a real life, or just the brief, brilliant dream of a mind that never was? The answer might not just redefine you, it could rewrite the universe. Imagine plucking a guitar string. The pitch changes depending on how tightly it's stretched and where your fingers press. Now picture that same principle governing the fundamental building blocks of reality. According to string theory, the universe isn't made of point-like particles but unimaginably tiny, vibrating strings, each oscillation producing a different note that manifests as particles and forces. An electron isn't a dot, it's a string humming one tone while a quark sings another. In this symphony of the cosmos, the laws of physics might just be the harmonies emerging from these microscopic vibrations. But there's a catch for the math to work. These strings can't just dance in the 3 dimensions we experience. They need room to move, requiring at least 6 extra dimensions curled up so tightly we'll never perceive them. Picture an ant crawling on a telephone wire. From far away, the wire looks one-dimensional, but up close, the ant can circle its surface, revealing a hidden second dimension. Similarly, our universe might be threaded with microscopic loops and folds, dimensions coiled smaller than an atom, shaping the string's vibrations, and thus reality itself, in ways we're only beginning to fathom. String theory's grand promise is its ability to unite quantum mechanics and gravity, 2 frameworks that have stubbornly resisted reconciliation. In this framework, gravity isn't a force transmitted by particles, but a byproduct of strings resonating in higher dimensions, like echoes in a cavern. It's as if Einstein's space-time and the quantum world have been speaking different dialects of the same language all along, and strings are the Rosetta Stone. Yet for all its elegance, the theory faces a glaring hurdle. How do we test it? If extra dimensions exist at scales a billionth of a billionth the size of an atom, conventional experiments can't reach them. Some physicists propose hunting for cosmic fingerprints, subtle gaps in particle collisions that hint at hidden dimensions, or gravitational waves carrying whispers of string-like structures. Others speculate that if these dimensions aren't perfectly compact, their influence might bleed into our world, slightly altering how particles behave at extreme energies. The most poetic possibility is that the universe isn't just governed by music, it is music. From the spin of electrons to the orbits of planets, everything could be part of an intricate composition written in vibrations we're only learning to hear. And if that's true, then the cosmic silence we perceive might just be a symphony playing in a key beyond our current perception, waiting for the right instruments to decode its deepest notes. Loop quantum gravity offers a radically different vision of reality, one where space isn't smooth and continuous, but stitched together from tiny, indivisible threads. Imagine the universe as a cosmic tapestry, woven from billions of microscopic loops, each one a fundamental stitch in the fabric of space-time. Unlike string theory's vibrating strings, these loops don't move through space, they are space, intertwining to create the very stage on which particles and forces perform. It's as if the pixels on your screen weren't just displaying an image but were the canvas itself, with every interaction adding a new thread to the weave. What's revolutionary about this idea is how it handles gravity. In Einstein's general relativity, gravity emerges from the curvature of space-time, like a bowling ball warping a trampoline. But loop quantum gravity takes this a step further, suggesting that space-time itself has a quantum structure, a granularity that becomes apparent at the smallest scales. Picture a digital photo, zoom in far enough, and you'll see individual pixels. Similarly, if you could peer into the heart of a black hole or the first moments of the Big Bang, you might find space-time dissolving into a shimmering network of these loops, each one carrying a tiny bit of gravitational information. This could solve one of physics' most vexing problems, the singularity. In classical physics, black holes crush matter into an infinitely dense point where the laws of physics break down. But in loop quantum gravity, there's no such thing as infinite density, just a tightly knitted web of loops that reaches a maximum tension and then bounces back. It's like stretching a rubber band until it snaps, except here, the snap isn't destruction, it's transformation. Some models even suggest that a collapsing black hole could rebound as a white hole, spewing out the matter it once devoured, or that the Big Bang wasn't a true beginning but the echo of a previous universe's collapse. The implications ripple outward. If space-time is quantized, then the smooth, continuous universe we experience is an illusion, a kind of cosmic averaging effect, like mistaking a fast-spinning fan blade for a solid disk. Even time, that relentless forward march, might emerge from the changing relationships between these loops, like a movie pieced together from individual frames. This could explain why time seems to flow at different rates near massive objects, not because space-time bends, but because the underlying network stretches and knots in new configurations. Yet for all its elegance, loop quantum gravity faces its own mysteries. How do these abstract loops give rise to the familiar three-dimensional world we inhabit? Why does gravity appear so weak compared to other forces? And most crucially, how do we test it? Some scientists are searching for subtle fingerprints in the cosmic microwave background, the afterglow of the Big Bang, which might bear the scars of spacetime's quantum origins. Others are studying black holes, hoping to detect echoes of their granular structure in gravitational waves. What's undeniable is that loop quantum gravity forces us to rethink reality at its core. If space is a network and time a consequence of its weave, then the universe isn't just in space-time, it is space-time, a dynamic, ever-evolving tapestry of relationships. And somewhere in those threads, the answers to our deepest questions might be waiting, knotted into the very fabric of existence. Consider the delicate balance of the cosmos, the precise strength of gravity, the exact charge of an electron, the perfect expansion rate of the early universe. Tweak any of these values even slightly, and stars wouldn't form, atoms would fly apart, or life as we know it would be impossible. This uncanny precision is what physicists call the fine-tuning problem, and it's one of the most baffling mysteries in science. Why does the universe seem tailor-made for our existence? The anthropic principle offers a deceptively simple answer. If it weren't, we wouldn't be here to ask the question. At its core, the anthropic principle is less an explanation and more a filter. Imagine flipping a coin 1,000 times and getting heads every single time. The odds are astronomically low unless you're only allowed to observe the result when it's heads. In that case, the outcome isn't surprising, it's inevitable. Similarly, we only find ourselves in a universe capable of sustaining life because, well, we couldn't exist in one that didn't. It's not that the universe was designed for us, it's that we're the accidental winners of a cosmic lottery, observing the one ticket where the numbers lined up just right. But some thinkers take this idea even further. If our universe's constants are the only ones that permit observers, could there be countless other universes where they didn't? This is the multiverse hypothesis, a sprawling landscape of alternate realities, each with its own unique physics. Most might be stillborn voids where gravity crushes everything instantly or where atoms never bond. In this scenario, we're not special. We're just the inevitable inhabitants of the rare universe where life got lucky. It's like standing in a vast desert and marveling at how perfectly the grain of sand beneath your foot fits, until you realize there are trillions of others where it didn't. Critics argue this is a cop-out, swapping one mystery for another. If we can't observe other universes, how is the multiverse any better than invoking a cosmic designer? Others propose a middle ground. Perhaps the laws of physics aren't arbitrary but emerge from deeper, undiscovered principles. A kind of cosmic DNA that inevitably generates life-friendly conditions. String theory's landscape of possible universes hints at this, suggesting our constants might be the result of higher dimensional geometry rather than blind chance. The most provocative twist comes from the participatory anthropic principle, which suggests that observation itself might shape reality. In quantum mechanics, particles exist in probabilistic states until measured, so could consciousness be the key that locks the universe into its life-permitting form. It's a dizzying thought. The universe isn't fine-tuned for us. We're fine-tuning it just by being here. Whether you see the anthropic principle as a profound insight or a tautology, it forces us to confront the strangeness of our place in the cosmos. Are we the unlikely beneficiaries of random chance, or is there a deeper logic woven into the fabric of reality? The answer might not just redefine our universe, it could redefine what it means to be alive within it. There's a quiet terror hidden in the fabric of reality, one that could erase the universe in the blink of an eye, not with fire or ice, but by rewriting the very rules of existence. It all hinges on something called the Higgs field, an invisible energy field that permeates all of space, giving particles their mass like a cosmic molasses, slowing them down. Without it, atoms would fly apart, stars would never ignite, and life as we know it couldn't exist. But what if this field isn't as stable as we think? What if, somewhere in the vastness of space, it suddenly slipped into a lower energy state, like a ball rolling from a hilltop into a deeper valley? The result would be vacuum decay, a cataclysm so absolute it makes black holes look quaint. Picture this: a tiny bubble forms where the Higgs field drops to its true minimum energy, a state where the laws of physics as we know them no longer apply. The walls of this bubble expand at the speed of light, rewriting reality in their wake. Atoms disintegrate, forces unravel, and the universe as we know it ceases to exist, replaced by something entirely alien. One moment you're sipping coffee on Earth, the next you and everything else are reduced to a chaotic soup of particles obeying new, unfathomable rules. The scariest part, you'd never see it coming. The bubble's edge would arrive without warning, erasing all traces of your existence before your neurons could even process the danger. Now, before you panic, here's the good news. The Higgs field appears to be remarkably stable. Experiments at the Large Hadron Collider suggest it's sitting comfortably in what's called a false vacuum, a temporary valley that could, in theory, last billions of years or longer. But stable doesn't mean permanent. Some theories propose that a sufficiently energetic event, a cosmic ray collision, a quantum fluctuation, or even an advanced civilization's experiment, could nudge the field over the edge, triggering the ultimate domino effect. It's like balancing a pencil on its tip. Given enough time, it will eventually fall. What's fascinating is how vacuum decay reflects the universe's precarious balance. The Higgs field's current state isn't the lowest possible energy configuration. It's just a local minimum, like a marble resting in a divot on a mountainside. The true ground state could be far below, and if the field ever tunnels through the barrier separating them, the consequences are irreversible. Unlike a supernova or asteroid impact, there's no surviving vacuum decay. No distant corner of the universe would be safe, no arc big enough to outrun it. The destruction wouldn't just be physical, it would be ontological, altering the very meaning of matter, energy, and time. Yet there's a strange beauty in this doomsday scenario. It reminds us that the universe isn't just unpredictable, it's fundamentally unstable, a house of cards built on quantum probabilities. The same field that makes life possible could, under the right conditions, erase it without a trace. And that's the paradox. Our existence hinges on a cosmic gamble, a fleeting equilibrium in an endless sea of possible states. So the next time you look up at the stars, take comfort in the fact that they're still shining, because somewhere out there, the dice are always rolling, and for now, they've landed in our favor. The Big Bang wasn't a beginning, it was a collision. That's the radical premise of the ekpyrotic universe theory, which reimagines our cosmic origin story, not as a fiery explosion from nothingness, but as a dramatic crash between two vast, sheet-like dimensions floating in a higher dimensional space. Picture two enormous panes of glass drifting toward each other in some unseen void. When they meet, the impact sends shockwaves rippling through their surface's energy that, in this model, becomes the seeds of galaxies, stars, and everything we know. No singularity, no infinite density, just a transfer of energy so colossal it births an entire cosmos. This idea hinges on brains, short for membranes, theoretical objects from string theory that could exist in up to 11 dimensions. Our entire universe might be confined to one such brain, like a painting trapped on a canvas, utterly unaware of the gallery around it. Meanwhile, parallel brains could hover mere millimeters away in higher dimensional space, separated by a gap we'll never perceive. In the ekpyrotic scenario, these brains occasionally collide, not with the violence of a car crash, but with the precise, cyclical rhythm of cosmic clockwork. Each collision resets the universe, scattering energy that cools into matter, igniting a new Big Bang-like event without the paradoxes of a true singularity. What's mesmerizing about this model is how it sidesteps some of cosmology's stickiest problems. The uniformity of the cosmic microwave background, the near-identical temperature of the universe in all directions, has long been explained by inflation, a period of exponential expansion in the universe's first moments. But the ekpyrotic theory offers an alternative. If our brain was stretched flat and smooth before the collision, like dough rolled thin, the impact would naturally distribute energy evenly across its surface. No inflation required. Even the universe's controversial dark energy could find an explanation here, not as some mysterious force, but as the gentle tug of another brain slowly drawing near, setting the stage for the next collision. The implications spiral outward. If this model holds, the Big Bang wasn't a one-time event, but the latest in an endless cycle of cosmic rebirths. Each cycle could last trillions of years, with brains drifting apart, gathering energy, and crashing together anew, a universe with no true beginning or end, only phases. It's a vision that echoes ancient myths of cyclical time, but with equations to back it up. And if other brains exist, each collision might spawn a universe with entirely different physics, making our laws of nature just one accidental outcome in an infinite series of possibilities. Critics point out the challenges. Brains and extra dimensions remain unproven, and the theory struggles to explain certain features of particle physics. Yet the elegance of the idea is undeniable. It transforms the Big Bang from a mysterious starting pistol into a note in a grander symphony, one where the universe isn't just expanding, but dancing, locked in an eternal waltz with dimensions we can't see. So the next time you hear about the birth of the cosmos, ask yourself, are we the first verse or just the latest refrain in a song that's been playing forever? Time crystals sound like something ripped from a science fiction novel, but they're very real, and they defy everything we thought we knew about the nature of matter. Unlike ordinary crystals, which repeat their atomic patterns in space like the symmetrical lattice of a diamond, time crystals repeat in time, oscillating between states without any energy input. It's as if you could wind up a clock once and have it tick forever, never running down, never obeying the second law of thermodynamics. This isn't perpetual motion. It's a bizarre new phase of matter that exists in a constant dance between order and chaos, rewriting the rules of physics as we know them. The discovery of time crystals sent shockwaves through the scientific community because they seem to break one of nature's most sacred principles, the arrow of time. Normally, systems tend toward disorder. Ice melts, coffee cools, and energy dissipates. But time crystals flip this script, returning to their original state over and over like a never-ending loop. Imagine a droplet of water that freezes, melts, and refreezes indefinitely without any change in temperature. That's the essence of a time crystal, a structure that pulsates in a predictable rhythm, not because it's driven by external forces, but because it's fundamentally locked into a cycle that even the universe's march toward entropy can't disrupt. How is this possible? The secret lies in quantum entanglement, the same phenomenon that links particles across vast distances. In a time crystal, atoms become entangled in such a way that their collective behavior creates a self-sustaining oscillation. It's like a row of dominoes that, instead of falling in one direction, continuously knock each other back and forth, never settling into equilibrium. Researchers first created these structures in the lab using chains of ions or specially arranged diamonds, coaxing them into this strange state with precise laser pulses. The result, a system that ticks like a clock but never winds down, existing in a perpetual quantum ballet. The implications are staggering. Time crystals could revolutionize quantum computing by providing ultra-stable qubits, the building blocks of quantum information, that resist the decoherence plaguing current systems. Picture a quantum computer that doesn't succumb to random errors, its calculations unfolding with the reliability of a metronome. Beyond technology, these crystals might hint at deeper layers of reality. Some theorists speculate they could be evidence of hidden temporal dimensions, where time doesn't just flow forward but folds back on itself in ways we can't yet perceive. Others wonder if they're glimpses of a universe where the distinction between past, present, and future isn't as rigid as we think, the most tantalizing possibility. Time crystals might be proof that the universe itself operates in cycles far grander than we've imagined. If matter can oscillate endlessly without energy loss, could the cosmos be doing the same on a larger scale? It's a radical thought, one that blurs the line between physics and philosophy, between the tangible and the theoretical. For now, time crystals remain a laboratory curiosity, but their very existence is a reminder that reality is far stranger and far more mutable than we ever dared to dream. The black hole information paradox isn't just a puzzle, it's a full-blown crisis at the intersection of quantum mechanics and gravity, threatening to unravel our understanding of reality itself. At its heart lies a simple but devastating question. When matter vanishes into a black hole, what happens to the information it carried? Quantum mechanics insists that information can never be truly destroyed. It might get scrambled, but it can't disappear. Yet black holes, those cosmic vacuum cleaners, seem to erase it completely. The moment something crosses the event horizon, it's lost forever, crushed into the singularity where even the laws of physics break down. This contradiction isn't just academic. It's a glaring sign that our theories of the universe are missing something profound. Enter Hawking radiation, Stephen Hawking's revolutionary insight that black holes aren't entirely black. Quantum fluctuations near the event horizon allow particles to escape over time, causing the black hole to slowly evaporate. But here's the catch. Hawking's math suggested this radiation is random, carrying no trace of the information swallowed by the black hole. If that's true, then when the black hole finally vanishes, the information it once contained is gone for good, violating quantum mechanics' sacred principle of information conservation. Physicists call this the information paradox, and it's been keeping them up at night for decades. Desperate for solutions, researchers have proposed some wild ideas. One is the holographic principle, which suggests that all the information falling into a black hole isn't lost, it's smeared across the event horizon like a cosmic hard drive. Picture a book burned to ashes. In this scenario, the words aren't destroyed, they're just encoded in the smoke. Similarly, the black hole's surface might store a perfect, if scrambled, record of everything it's ever consumed. When Hawking radiation escapes, it could carry fragments of that data, slowly leaking the universe's secrets back into existence. Then there's the firewall hypothesis, an even more radical fix. If information can't escape the black hole but must somehow be preserved, quantum mechanics might demand a blistering wall of energy just inside the event horizon, a literal firewall that incinerates anything falling in. This would prevent information from ever reaching the singularity, preserving it in the radiation. But there's a problem. Einstein's general relativity says crossing the event horizon should be uneventful, like floating into a fog. A firewall would violate that principle, forcing physicists to choose between quantum mechanics and relativity, a Sophie's choice no one wants to make. The stakes couldn't be higher. If information truly vanishes in black holes, it means our universe operates with a fundamental amnesia, erasing its own history in cosmic sinkholes. But if it somehow survives, hidden in Hawking radiation or holographic codes, then reality might be far more interconnected than we imagined, a place where nothing is ever truly lost, just transformed. Every observation of distant black holes, every ripple of gravitational waves brings us closer to an answer, and when we find it, we won't just solve a paradox. We'll rewrite the rules of existence itself. Every second, trillions of nearly massless particles stream through your body, right now without a trace. These are neutrinos, nature's most elusive cosmic specters, capable of passing through light years of lead without a single collision. Born in the hearts of stars, the fury of supernova, and even the decay of atoms in your bones, they're everywhere and nowhere, a constant whisper in the background of reality. But don't let their ghostly nature fool you. These tiny particles might hold the answer to one of the universe's biggest mysteries. Why does anything exist at all? Here's the puzzle. When the universe began, matter and antimatter should have been created in equal amounts, annihilating each other in a flash of energy that left behind nothing. Yet somehow, a tiny surplus of matter survived one extra particle for every billion annihilations. And here we are. The question is, what tipped the scales? Neutrinos, with their bizarre quirks, might be the missing piece. Unlike most particles, they oscillate between flavors electron, muon, and tau as they travel, morphing identities like cosmic shape-shifters. This behavior hints at something profound. Neutrinos might be their own antimatter counterparts, a property that could have allowed them to decay asymmetrically in the early universe, favoring matter over antimatter in those critical first moments. Imagine the early cosmos as a grand cosmic bakery, where matter and antimatter were batter being mixed in perfect balance, but neutrinos, though slippery, barely their ingredients could have been the uneven stir that left just a bit more batter in the bowl. If they violated what's called charge parity symmetry, decaying slightly more often into matter than antimatter, that infinitesimal bias might have cascaded into the universe we see today. It's a delicate dance of physics where the tiniest imbalance in the smallest particles snowballed into galaxies, planets, and life itself. The stakes couldn't be higher. Experiments like Japan's Super Kamiokande and the upcoming Deep Underground Neutrino experiment are hunting for clues, watching for subtle differences in neutrino behavior that could confirm their role as cosmic matchmakers. Some theories even suggest that neutrinos' elusive masses so small we still don't know their exact values could be tied to forces we've yet to discover, hidden threads woven into the fabric of reality. But here's the twist: neutrinos might not just explain why we exist. They could be sculpting the universe even now. As the lightest known particles with mass, they zip through the cosmos at nearly the speed of light, their collective gravity subtly tugging at the web of dark matter that binds galaxies together. They're the universe's quiet architects, shaping structures too vast to comprehend while remaining nearly invisible to our detectors. So the next time you feel the sun on your skin, remember, you're also being bathed in neutrinos from its core, particles older than the solar system itself. And somewhere in their ethereal dance lies the answer to why there's something rather than nothing, a secret written in the faintest ink, waiting for us to decipher it. Somewhere beyond the Milky Way's starry veil, an invisible leviathan is pulling entire galaxies toward it with the force of 1 trillion suns. Astronomers call it the Great Attractor, a gravitational anomaly so powerful it's dragging our local group of galaxies, including the Milky Way, toward it at 14 million miles per hour. Yet despite this colossal influence, we can't see it directly. Our view is blocked by the thick dust and stars of our own galaxy's disk, leaving scientists to piece together its nature through subtle distortions in the cosmic web. What makes this mystery so compelling isn't just its hidden location, it's the sheer scale of the puzzle. The Great Attractor's pull suggests a mass equivalent to tens of thousands of Milky Ways, yet scans of the region reveal only partial explanations. The Norma Cluster, a dense gathering of galaxies about 250 million light-years away, seems to anchor part of this gravitational sinkhole. But here's the catch: even combined with surrounding superclusters like Laniakea, the cosmic metropolis our galaxy calls home, the math still doesn't fully account for the observed motion. There's something else lurking in the shadows, something massive enough to bend the trajectories of galaxies like a cosmic whirlpool. Some theorists propose an even wilder possibility. What if the Great Attractor isn't just a cluster of matter, but a wrinkle in spacetime itself? Einstein's general relativity allows for regions where the fabric of reality could be warped in ways we don't yet understand, like a hidden downhill slope in the universe's geometry that everything naturally slides toward. Alternatively, it might be the fingerprint of something beyond our current physics, perhaps a remnant of the universe's early asymmetry or a gravitational echo from a collision with another universe during inflation. The hunt for answers is pushing telescopes to their limits. X-ray observatories peer through the Milky Way's dust, revealing hot gas swirling around unseen masses, while radio surveys map the peculiar motions of thousands of galaxies. Each new dataset adds pieces to the puzzle, yet the full picture remains tantalizingly out of reach. One thing's certain: as we decode the Great Attractor's secrets, we're not just mapping a distant anomaly, we're rewriting our understanding of how matter, energy, and spacetime conspire to shape the grandest structures in existence. So the next time you look up at the night sky, remember, you're not just seeing stars, You're witnessing an epic cosmic tug of war, with our entire galactic neighborhood caught in the grip of forces we're only beginning to comprehend. And somewhere beyond that shimmering band of the Milky Way, the universe's greatest unseen hand is still pulling the strings. Quantum gravity represents the final frontier in our quest to understand reality, a theory that could stitch together the cosmic and the quantum, revealing the universe's deepest blueprint. For over a century, physics has been split between two titanic frameworks: Einstein's general relativity, which paints gravity as the curvature of space-time by massive objects, and quantum mechanics, which governs the chaotic, probabilistic dance of particles at the smallest scales. Both work flawlessly in their respective domains, but when they collide, like near a black hole's singularity or at the Big Bang's inception, the equations break down into gibberish. It's as if the universe speaks two mutually incomprehensible languages, and we're stuck in the middle, desperate for a translator. String theory emerged as one ambitious contender, proposing that all particles are vibrations of infinitesimal strings in a 10-dimensional reality. In this symphony of the cosmos, gravity wouldn't be a standalone force but a harmonic resonance emerging from these strings' interactions. The elegance is undeniable except for one glaring hitch. Those extra dimensions are curled up so small that no experiment has yet glimpsed them. Without empirical validation, string theory remains a breathtaking mathematical daydream, its beauty untethered from observable proof. Meanwhile, loop quantum gravity takes a radically different approach, suggesting space-time isn't smooth and continuous but woven from discrete, interlocking loops. Imagine the universe as a tapestry where each thread carries a tiny quantum of area or volume. Black holes and the Big Bang wouldn't be singularities but knots in this fabric, places where the weave tightens to its limit and rebounds. The theory's boldest claim, time itself might be an illusion, emerging from the changing relationships between these loops like frames in a film strip. Yet, like string theory, it struggles to make predictions testable with current technology, leaving physicists in a frustrating limbo. The stakes couldn't be higher. Without quantum gravity, we can't explain what truly happens in the universe's most extreme environments. Take black holes. Relativity says they trap everything behind an event horizon, while quantum mechanics insists information can't vanish. The clash reveals a schism at reality's core. Even attempts to probe the Planck scale, the unimaginably tiny realm where quantum gravity should dominate, run into walls. The energies required to observe such phenomena are billions of times beyond what our particle colliders can muster, as if we're trying to decode a whisper from across an ocean. Some researchers are hunting for indirect clues. Gravitational wave detectors might catch echoes of quantum spacetime's granularity in the ripples from colliding black holes. Others scrutinize the cosmic microwave background for anomalies that could hint at gravity's quantum origins. And then there's holography, the radical notion that our 3D universe is a projection from a 2D boundary, with gravity somehow encoded in that lower dimensional surface. If true, it would mean the cosmic fabric isn't just mysterious, it's an elaborate illusion, a cosmic sleight of hand we're only beginning to suspect. The search for quantum gravity isn't just about filling textbooks. It's about uncovering whether the universe is fundamentally continuous or pixelated, whether time is real or emergent, and whether black holes are cosmic dead ends or portals to something stranger. Until we crack this puzzle, the fabric of reality remains half-written, its deepest truths hovering just beyond our grasp. And when we finally piece it together, we won't just solve equations, we'll rewrite the story of existence itself. The cosmic microwave background, the afterglow of the Big Bang, should be a chaotic, random fingerprint, a uniform tapestry of hot and cold spots scattered like confetti across the sky. Yet when scientists mapped it with unprecedented precision, they stumbled upon something eerie, a strange alignment of anomalies nicknamed the Axis of Evil. This mysterious pattern defies the odds, as if the universe rolled a die 1,000,000 times and got the same number every time. Cold spots cluster along one axis, hot spots along another, forming a peculiar cosmic axis that points roughly toward the constellations Leo and Aquarius. Statistically, this shouldn't happen. So is it just a fluke, or is the cosmos trying to tell us something? One possibility is that this alignment is nothing more than a trick of perspective, a cosmic mirage caused by our imperfect view from inside the Milky Way. Dust, magnetic fields, or even the galaxy's motion could subtly distort the microwave background, creating the illusion of structure where none exists. But here's the unsettling part. Even after accounting for these local effects, the anomaly persists. It's as if we peeled back the curtain on a stage, expecting to find the machinery behind the illusion, only to discover the mystery runs deeper than we thought. Then there's the radical alternative. What if the Axis of Evil is a relic of something older than the Big Bang itself? Some theories suggest our universe wasn't born in isolation, but emerged from the collapse or collision of a previous cosmos. In this scenario, the alignment could be a scar, a gravitational imprint left by whatever came before, like a fingerprint pressed into wet clay before it hardened into the universe we know. Others speculated hints at a preferred direction in space-time, a cosmic grain that breaks the fundamental assumption that the universe looks the same in all directions. If true, it would mean the cosmos isn't just expanding. It might have a subtle tilt, a hidden asymmetry woven into its very fabric. The implications are staggering. Modern cosmology rests on the principle of isotropy, the idea that the universe has no special direction, no up or down on the largest scales. The Axis of Evil challenges that foundation, suggesting the cosmos might not be as uniform as we thought. It's like discovering that what you thought was a perfectly smooth tabletop actually slopes imperceptibly in one direction, tilting everything on it in ways you never noticed. Skeptics argue the alignment could still be a statistical anomaly, a 1 in a million coincidence that only seems meaningful because we're here to observe it. But as telescopes gather more data, like the upcoming LightBird mission, designed to scrutinize the microwave background with even finer resolution, we'll soon have the evidence to settle the debate. If the Axis of Evil is real, it won't just be a curiosity. It could rewrite the first chapter of cosmic history, revealing that the Big Bang wasn't the true beginning, just the latest act in a story far older and stranger than we ever imagined. Picture a star moving so fast it could cross the distance from Earth to the Moon in just 15 minutes, a cosmic bullet hurtling through the void at over 1,000,000 miles per hour. These aren't science fiction creations. They're hypervelocity stars, lone wanderers flung from their home galaxies with such force that gravity itself can't reel them back in. Unlike most stars bound in the orderly dance of spiral arms or globular clusters, these renegades streak through the darkness between galaxies, leaving everything familiar behind. And their origin stories are as violent as they are fascinating, cosmic catapults powered by the universe's most destructive forces. At the heart of this mystery lie supermassive black holes, the invisible monsters lurking in galactic centers. When a binary star system, two stars orbiting each other, wanders too close to one of these gravitational behemoths, chaos ensues. The black hole's immense tidal forces rip the pair apart, capturing one star while flinging the other outward at unimaginable speeds. It's like a slingshot effect on a galactic scale, where the energy stolen from the black hole's rotation becomes the launching mechanism. The ejected star doesn't just drift away, it's shot into intergalactic space like a pebble from a cosmic sling, destined to wander the void alone. But black holes aren't the only culprits. Some hypervelocity stars might be survivors of dwarf galaxies torn apart by their larger neighbors, their chaotic orbits transformed into one-way tickets into the abyss. Others could be the remnants of supernova explosions in binary systems, where the sudden loss of a companion's mass sends the surviving star careening like a snapped rubber band. Each scenario leaves a unique fingerprint in the star's speed, trajectory, and even chemical composition, offering clues to the violent events that shaped its journey. What's truly astonishing is how far these stars travel. While most stars spend their lives orbiting the galactic center, hypervelocity stars break free entirely, crossing the vast, empty stretches between galaxies. Imagine a ship cast adrift in the ocean. Only the ocean is millions of light years wide, and the ship is a blazing sphere of plasma with no harbor in sight. Some might even escape their home galaxy cluster entirely, destined to drift forever in the cosmic wilderness, their light fading into the endless dark. Yet these orphaned stars aren't just celestial curiosities, they're cosmic breadcrumbs, revealing secrets about the galaxies they left behind. By tracing their paths backward, astronomers can map the gravitational fields of distant black holes, even inferring the presence of hidden mass or unseen mergers. Their speeds serve as a measuring stick for the forces that shaped them, offering a unique window into the most extreme environments in the universe. And because they're so isolated, their light reaches us unpolluted by the glow of nebulae or star clusters, making them pristine laboratories for studying stellar chemistry and evolution. The next time you look up at the night sky, remember, among those twinkling points of light, there might be a runaway, a star fleeing its birthplace with such ferocity that it's left the galaxy behind. These cosmic outcasts remind us that the universe isn't just a place of order and symmetry, but of chaos and upheaval, where even the most stable systems can be shattered in an instant. And somewhere out there, in the black between galaxies, countless more are racing onward, their stories written in speed and solitude, waiting for us to decode them. Galaxies might seem like serene islands of stars, floating peacefully in the cosmic ocean, but the truth is far more dramatic. Out there in the darkness, a relentless game of cat and mouse unfolds on a scale almost impossible to comprehend, what astronomers call galactic cannibalism. Larger galaxies, driven by their immense gravity, consume their smaller neighbors, growing more massive with each meal. It's not a quick, violent process, but a slow, inevitable feast stretching across billions of years. And here's the spine-tingling part. Our own Milky Way is no innocent bystander, it's a seasoned predator, its history written in the ghostly trails of stars it's torn from its victims. These remnants, known as stellar streams, are the cosmic equivalent of breadcrumbs left behind after a meal. Picture a galaxy like a spider at the center of a web, except instead of silk, its gravity stretches out invisible tendrils, pulling smaller galaxies apart. As they're digested, their stars are scattered into long, looping ribbons that orbit the larger galaxy like celestial tinsel. The Milky Way has left its mark on dozens of these smaller systems, with the most famous victim being the Sagittarius dwarf galaxy, once an independent entity, now reduced to a shimmering arc of stars wrapped around our galactic home. But why does this happen? It all comes down to gravity's relentless pull. When a smaller galaxy drifts too close to a larger one, tidal forces stretch and warp it, much like the moon's gravity creates ocean tides on Earth. Over time, these forces strip away stars, gas, and dark matter, funneling them into the larger galaxy's grasp. Some mergers are gentler, with the smaller galaxy's structure dissolving gradually. Others are more dramatic, like the impending collision between the Milky Way and the Andromeda Galaxy. a slow-motion crash that will eventually birth a new hybrid galaxy in about 4 billion years. What's fascinating is how these events shape galactic evolution. Every time a galaxy absorbs another, it doesn't just grow in size. It gains new material to forge stars, enriching its chemistry with elements from its prey. The Milky Way's outer halo, a diffuse region surrounding its bright disk, is essentially a graveyard of devoured galaxies, their stars now mingling with those born here. Even our solar system might owe its existence to this process. Some researchers speculate that past mergers triggered waves of star formation, setting the stage for the birth of our sun. The most haunting aspect, this cycle is never ending. Galaxies cluster together in vast webs, drawn inexorably toward one another by gravity. In dense regions like the Virgo cluster, this cannibalism happens faster, with giant ellipticals growing fat on a steady diet of smaller galaxies. In quieter corners of the universe, like our local group, the feasts are fewer but no less significant. And as the cosmos expands, galaxies will continue to merge, their fates intertwined in an endless cosmic dance of destruction and rebirth. So the next time you gaze up at the Milky Way's starry band, remember, you're not just looking at a collection of stars, you're witnessing the aftermath of a billion-year feeding frenzy, one that's still unfolding silently all around us. And somewhere out there, another galaxy may already be drifting too close, destined to become part of our own. The universe is running down, not with a bang, not with a whimper, but with the slow, inevitable fade of heat death. Picture trillions of years from now, when the last stars have burned out, black holes have evaporated, and all that remains is a thin, cold soup of particles drifting further apart with every passing moment. This is entropy's end game. A state where no energy gradients remain, no work can be done, and time itself becomes meaningless. Without change, without the rise and fall of temperature, motion, or structure, how could we even measure the passage of time? It's like trying to count the frames of a movie after the screen has gone dark. Yet there's a haunting beauty in this desolation. The heat-death scenario isn't chaos. It's the universe's ultimate equilibrium. A perfect stillness where every particle is maximally disordered, spread so evenly that nothing can ever happen again. But here's the twist. Even in this frozen oblivion, quantum mechanics whispers of possibilities. Empty space isn't truly empty. Virtual particles flicker in and out of existence, a seething foam of potential energy that defies the classical notion of a dead universe. Given enough time, and we're talking timescales so vast they make the current age of the cosmos seem like a blink, these fluctuations could, statistically, spawn a new Big Bang. It's the ultimate cosmic lottery. Roll the quantum dice enough times, and eventually you'll hit the jackpot of rebirth. This idea, known as the Phoenix Universe hypothesis, suggests that heat death isn't the end but a pause in an endless cycle of collapse and renewal. Imagine a dormant volcano, silent for millennia, until one day pressure builds and it erupts anew. In this view, our universe might be just one iteration in an infinite series, each one rising from the ashes of quantum noise in the void. Some theories even propose that the conditions for a new universe could be encoded in the very fabric of space-time, like a seed waiting for the right moment to sprout. But what if time doesn't just pause? What if it unravels entirely? In a universe where entropy has erased all structure, there's no arrow of time, no past or future, just an eternal present where nothing changes. Philosophers and physicists debate whether time is a fundamental property of the universe or an emergent phenomenon, a side effect of entropy's increase. If the latter is true, then in the heat death, time might not just stop, it could cease to have ever existed as a meaningful concept. The universe wouldn't be timeless, it would be outside of time, a frozen snapshot with no before or after. The most tantalizing question isn't whether the universe will end, but whether end is even the right word. Could the far future hold not oblivion, but transformation? Some models of quantum gravity suggest that the fabric of space-time might reconfigure itself, twisting into new geometries that reboot the cosmic clock. Others speculate that our universe is just one bubble in an infinite multiverse, where death here is irrelevant to the endless froth of creation elsewhere. So when we peer into the abyss of deep time, we're not just staring at our own mortality writ large. We're glimpsing the universe's deepest paradox, that even in stillness there's potential, and even in endings there's the ghost of a beginning. Whether the cosmos is destined for eternal silence or cyclical rebirth, one thing's certain: the story of time is far stranger and far more open-ended than we ever imagined. From the subatomic shimmer of quantum foam to the unfathomable vastness of parallel universes, our journey through these 30 mind-bending perspectives has revealed a cosmos that defies every expectation. The universe isn't just bigger than we imagined, it's stranger, filled with black holes that might birth new realities, dimensions curled into hidden knots, and particles that dance between existence and oblivion. Each mystery we've explored isn't just a gap in our knowledge, it's a doorway, inviting us to rethink everything we thought we knew about space, time, and the very fabric of existence. Consider this: every time science has peeled back a layer of reality, we've found deeper questions waiting beneath. Newton's clockwork universe gave way to Einstein's warped spacetime, which in turn dissolved into the probabilistic haze of quantum mechanics. Today, we're standing at the edge of another revolution where the answers might not just surprise us, they could rewrite the story of everything. The cosmic fabric isn't a static backdrop. It's alive with possibility, humming with dark energy, vibrating with strings, or perhaps even pixelated into holographic code. And the most thrilling part, we're only just beginning to scratch the surface. Think about how far we've come. A century ago, astronomers debated whether the Milky Way was the entire universe. Now we're mapping multiverses and probing the quantum vacuum for whispers of other dimensions. The tools we're building: gravitational wave detectors, quantum computers, telescopes that peer back to the Big Bang's afterglow, aren't just instruments. They're keys unlocking doors we didn't even know existed. Who's to say what we'll find next? Maybe evidence of a cyclic universe, forever collapsing and rebounding. Or signals from an alien civilization hidden in the static of pulsars. Or perhaps something so unexpected it'll make today's wildest theories seem quaint. This isn't just science, it's the ultimate adventure. Every time we point a telescope at the sky or smash particles in a collider, we're not just collecting data. We're exploring uncharted territory, venturing into the unknown with nothing but curiosity as our compass. And the best part, you're part of this story. Whether you're a scientist, a stargazer, or someone who just loves to wonder, you're witnessing humanity's greatest quest to understand our place in the cosmos. So as we wrap up this journey, let's not see it as an ending but a launching point. The universe has spent 13 billion years hiding its secrets. Now it's our turn to seek them out. What do you think lies beyond the edge of our understanding? Drop your boldest theories in the comments. After all, the next great discovery might start with a conversation. And if you're hungry for more cosmic mysteries, hit subscribe. The universe isn't done surprising us yet, and neither are we. Until next time, keep looking up and wondering.